Hello and welcome to Engineering Thoughts, where engineering minds come together to discuss topics of relevance and interest to our industry. I'm Vanessa Seeley-Fisher, and joining me today are industry experts John McEwan and Neil Webb. If you don't already, please do subscribe. And now on to today's topic. Today we're going to be addressing corrosion in mine waters. Now you may say, why are we interested in corrosion in mine waters and what difference is that to any other water? And those are relevant questions and we're going to start addressing them right away. So John, I know you've worked in the mining sector for many years, and I thank you that you're going to share some of this expertise with us today. Just to give us a framework here in South Africa, what sort of size are we looking at in terms of the South African mining industry?
Mining industry is still quite large. It's down from its heyday in the 90s, but it still makes a significant proportion. It's between 7.5% and 10% of the GDP. What's more significant is the fact that about 55 to 60% of the exports are mining. So it's a large foreign exchange earner.
And that's really important, especially here in South Africa. But I think the question about corrosion in mine waters is applicable not just here in South Africa. And I'd like some clarity on what defines a mine water. Where do we find it? Why is it special? So where do those waters start and what classifies them as mine waters?
South Africa is a water scarce country.
Yes.
It's 30th in the world of dryness. A lot of other mining companies are very similar. So what tends to happen is that you tend to rely on reuse of water in mines rather than fresh water, unlike once-through systems, etc. The vast majority of water in this country is used by the agriculture. It's about 60%. You tend to find in developed countries a lot more water is used for agriculture, a lot less in non-developed countries. So we're a partially developed country and agriculture uses a lot. However, it's very intermittent, very unpredictable, the rain. It's very low. It's about half the global average. And it tends to be in areas of high rainfall. So Mpumalanga's got a lot more than the Northern Cape and the Northwest.
Right.
Which are the areas that tend to have a lot of the mining, etc. So it causes water stress, both in terms of shortage of water, but also in terms of competition with domestic. And that can create local problems, etc. But that's for another issue.
Absolutely.
But the mines tend to use the same water and reuse when they can because it's an expensive commodity.
But John, that water that is used in the mining industry, are we talking about water that is used underground or water that is drawn from underground or water that is used in the mineral processing aspect of the material that we actually extract from the mine? I mean, those are actually three different aspects of water in the mining industry.
And that's one of the problems, one of the main problems. The vast majority of water that's used in the mining industry is reused water. Underground, it's used for running equipment, washing down, cooling, because the temperature underground, particularly at Monaneng, is what, in the high 50s. So a huge amount of cooling's got to go. You either do that by putting refrigeration plants underground, or you do that by pushing ice down pipes and then recollecting the water. But what happens in the end, the water always finds its way to the bottom of the mine. And that's where it is collected, treated to a certain extent, and then pumped back up again for either reuse in the mine or use on surface. So as you know, Neil, there's an awful lot of water used in a lot of different areas on the surface. It could be boiler water. It could be moving tailings, which are the waste material to a tailing dump. It could be for the actual dissolving chemicals for doing the refining and doing the solutions. There's an awful lot. And that water is fairly critical in terms of its composition, whereas in mine waters used underground is less critical, apart from pH, which we will get into later on.
Yeah. But John, I remember getting involved in the construction of new mine shafts back in the 80s, where the steelwork associated with the mine shaft was primarily galvanized. And on one occasion, we did a shaft inspection where, looking back on it, it's quite horrific. We stood on the top of the Mary Ann with a tin hat over the top of us and a naked acetylene flame for light and we got lowered down the shaft to inspect the condition of the steelwork. They call them buntons, which are the name that is used to describe the steelwork that supports the guides that the cages and skips and so on run in. And it was quite interesting. I mean, the water was pouring down the shaft from up top, and that was seepage water that had come out of the rocks. And the tops of all of these steel components were completely worn away. When I say worn away, the galvanizing on the top of these things had been worn away by the action of the water falling down over the top of these beams. But what makes that water, that seepage water that comes out, what characteristics of that water make it so aggressive?
You were lucky to be on top of on the Marianne. I was hanging in a little cobble underneath, with just almost like a little bucket, and you couldn't get your feet straight because there was only about that much room, flat surface, right, etc. But we didn't rely on oxyacetylene torches. We actually had lights. But the other problem is, of course, is communication, because the only way you can communicate is through the wire rope. You can't communicate any other way.
So you're pulling on it.
So you've got, anyway, that's another. Stop, please, stop. Yeah, I understand that. There's an awful lot of salts in the rock and the ore. Right. And what happens with this seepage water is, if you look at Sands water quality, it allows an awful lot of total dissolved solids. It's about 1,200 ppm, which I think is ridiculous, but that's another issue. Even if you use fresh water from the local river, Safal River, or from the Chreep or whatever, eventually that seeps through the rock. That rock leaches out chlorides, particularly in the Free State, but also it reacts with various other components in the ore, the worst of which is what's known as iron pyrites or fool's gold, because it's the same color as gold. And when gold was first found in America, people thought it was gold, but it wasn't gold. So that now reacts with water. The sulfide ore reacts with water to form sulfates and to form soluble iron and to form acidity. Right, and that's the problem. Your pH can go from what's regarded as neutral in the 7 to 9 range to drop to below 4. And that's why mines are so corrosive. The other issue is the fact, in your point about the buttons, is that you get a poulticing effect, because you can get settlement of solids, dust that comes down. Right. Depends on whether it's a downdraft or an updraft shaft, etc. And they have different corrosivities. But that tends to settle on there. The water settles in there. It then dries and concentrates and dries and concentrates and dries and concentrates. And then it becomes more and more and more aggressive.
So you've actually got corrosion happening because of the water itself, and corrosion happening as a result of the dust and water interaction.
It's a combination.
And managing that becomes, I imagine, a nightmare.
It's very difficult because the constraints of doing a mine inspection, they're probably done late at night, early in the morning, once a week. They're statutory. The law says you must do a shaft inspection, etc. And I've been on many because I put samples on top of the buttons to look at how the materials went. And I must have put several hundred into at least a dozen mine shafts. So I've done several inspections. What they tend to do nowadays is redesign the button so it becomes an aerofoil rather than a flat surface. And they're called aerofoil buttons. That tends to help matters a little bit. But they're difficult to fabricate and more expensive. They're not difficult to galvanize.
John, in terms of the composition of the water that we're talking about, you've described it getting these high levels of salt that obviously will increase the conductivity of the water. And from your experience, is that the primary reason that the waters are so aggressive?
There are a number of factors that affect corrosion in water. Conductivity is one. The higher the conductivity, the better the electrical connection. Electricity is involved with corrosion. Yes. I don't want to go into the depth of it, but basically electricity is involved. Yeah. So the better the conductivity, the more electrical it is, the higher the corrosion rate. But on average, to increase the conductivity from 100 ppm to 1,000 ppm will probably double or maybe at most treble. The other aspect is temperature. Corrosion rate can double in every 20 degrees. So when you're on the surface at 19 or 20 and you go underground, it's 56. And even with cooling, you can't cool everywhere, particularly the bottom of the shaft. It's a stagnant area, very little flow of air. It gets very, very hot and very, very humid, etc. But then again, corrosion rate doubles every 20 degrees or so. Other area is dissolved oxygen. Water can take up to 8 parts per million dissolved oxygen. An average mine water is probably anything between 4 and 7, partly because the higher the temperature and the higher the dissolved solids, the less oxygen can dissolve, and partly because it's being exposed and it's losing air, etc. But then again, dissolved oxygen probably only increases the corrosion rate by 3 or 4, maybe at most, from a DO2 of 2, you would very rarely get to 0, up to a dissolved oxygen of about 8. The main factor is acidity, because when you get a pH below 4, all of a sudden the corrosion rate just increases. It can go by 8, 9, 10.
So, John, given this highly aggressive environment of it's either effectively immersed in that you've got the water pouring down the shaft, so the surfaces are always wet, the humidity is high, high oxygen, high salts, low pH. It sounds like a recipe for a really, really aggressive corrosive environment. How do we address it? What magic coatings, for example, can one use, given that we have to make the shaft equipment out of steel? How can we protect the steel?
You mentioned galvanized, and that's very commonly used, particularly in the west towards the Free State, Clarksdorp area, partly because of it's convenient, the new mines. The difficulty of protecting corrosion is a number of fold. One, it's difficult to do in situ. Once the mine's working, there's limited time, limited access, everything's against you. The other issue is the fact that we as corrosion, I use the word loosely engineers, have one thought, and that is how do we reduce corrosion? It has huge costs to the mining industry. We haven't even covered that yet, have we?
Yeah.
What happens is that you as an engineer interested in corrosion, the mining engineers only got one interest, and that is getting the rock out. It's production.
Yeah.
The 7 engineers have got that. So you're in competition with them. You come down and you're a waste of time. You have your meetings with the top echelons. You have all these engineering manager meetings, mine manager meetings, and you say X, Y, Z, and they say, okay, nod sagely, but nothing ever gets done. So they tend to manage the problem. They'll splash paint on if they feel they can do. They might use a bitumistic paint, which has got its advantages because it sticks very well to a rusty surface and also is very tolerant of wear. Because the big problem of putting a coating on structures underground is wear and damage. Because miners throw pipes around. They don't
carry them with
Carry
care.
them.
it's not
And there's falling rock.
and then it gets damaged, etc. So, yeah, but there are a number of modern coatings that go in. Galvanized is used extensively in shaft steel work and station steel work, ducting underground, etc. That's usually, and it works very, very well because the zinc protects the steel afterwards. So even if you get breaks in the zinc, you get protection, which you don't get with a paint coating, etc. Paint coatings that are used a lot, and I've done some research on this, are very rare, and they're only in areas where they can be controlled. Epoxy is used quite often underground. Alkyds are used extensively because they're very easy to put on, etc. But there's no real magic coating because of the damage that can occur during handling and during service. That's why galvanized is so good, because it actually protects the damaged areas.
Yeah. But John, I remember the late Walter Barnett being very involved in the development of duplex coatings, where we added a polymeric coating onto the galvanizing to protect the galvanizing predominantly from either wear or perhaps in the high chloride environments where you have soluble corrosion products. And there was a kind of a progression that up at the top of the shaft you had galvanizing only. As you went down the shaft, and in the bottom lower areas you would then get the addition of these either epoxies or polyurethanes or whatever material was developed to provide what was called the duplex coatings. At the time they were considered to be successful, but what makes that success?
Well, the big advert for that was the synergy that occurs between the two coatings. So galvanizing may improve corrosion rate by a factor of 3, coating may improve it by a factor of 1.5, but together they become 12 or 13. Right. And that's the idea, because one supports the other. It's all like synergy. It's like having a roundtable discussion. You usually talk about more things because somebody's always got another idea, right, etc. And that's the main reason why. It has the benefit that even if you damage the coating, and they tend to use an epoxy coating because there are several coatings you can't use with galvanized, and even if that's damaged, even if that gets a poultice effect on a bunton, that will wear away or corrode away, but the galvanized will protect. Some of the work I did on bunting steel was even a minor stainless steel corroded very, very badly. We're talking about millimeters per year for a 12% chromium stainless steel. The other steel was about 5 times more, but the galvanized seemed to do quite well, although it was far worse because this poultice effect actually... Right. But it's horses for courses. It depends on the area. You can easily paint something underground that is not being immersed all the time,
Yes.
you cannot do the same when you're running equipment and when you've got a mine shaft.
John, you alluded a little earlier to newer mines, and I wondered whether you'd seen a difference in approach with perhaps more of a corrosion thought behind it when they start a new mine. Do they take corrosion into greater consideration than the older mines where that wasn't perhaps given thought initially and now it's all a retrofit?
That was certainly, as Neil said, in the 80s and 90s when those shafts that were in those days JCI shafts, and there was Walter and Bob Andrew. You remember
Yes.
Bob? Bob was the corrosion engineer, and he had an awful lot of influence in terms of design, and
Right.
that tended to happen with the new shafts. Today, I think less so. I think people are mining in the gold, for instance. Let's use gold as an example. 3 to 5 grams per ton of gold. You know, gone are the days where you're mining 10 to 12, 15. Yes. Gone are the days where you leave huge amounts in pillars to support the roof. You pick and choose what you do. And even though they listen sagely to an engineer, a corrosion engineer, I think often it's the bottom line. If it's costing twice as much, and that's the problem with duplex. Galvanized would be 1.5 to 2 times the price of steel. A duplex would be 3 to 5 times. Right. And that's where the problem comes.
And then it, of course, is capital cost as opposed to long-term life cycle costing, because that's something that appears not to happen in the mines, is life cycle costing. You run it until it breaks and then you replace it.
Exactly. And in my days at Mintech, we used to sort of always hold the hammer, it's the life cycle costing, like, oh, look at this. But basically a mine engineer has only got one idea, and that is, I'm working now, I want to get the production, I want to make the profit. It's somebody else's problem further down the line. I'm now no longer a section engineer. I've now become a senior engineer, and therefore somebody else can have the problem. It's the same problem with wire ropes. They're looked after only because of safety. They're not bothered about other things because they can easily be replaced.
Yeah. John, you've alluded a couple of times to area. We have, just again going to gold, we have gold production spread across a wide area in South Africa. And of course, we also have other types of mining, which are in remote areas, or remote from the Witwatersrand. But are the corrosion conditions different in different areas of the country, depending on the rock strata and so on?
The big kicker on the block now is platinum group metals. That makes up 50% of the export earnings. And the next one's coal. Platinum group metals, South Africa is still number 1 in the producer. Coal was number 3. So we're still fairly high up. The other one that has a fair amount is gold. All of them have got pyrite. All of them are associated with pyrite. So whether or not you've got an underground mine where you've got the Fisher water, or whether you've got coal washing plants where you wash the coal down for export quality, all those tailings get taken off, they go into a tailing dump, all the water becomes more and more acidic. And in that case, unlike underground mines where the water is recycled and tried to reuse and occasionally goes to discharge into rivers and causes problems, there, most of it goes into the local areas. So you get pollution of groundwater in that area, pollution in the rivers. And that's the problem with the coal industry. That's particularly in the Mpumalanga area. In the platinum mines, they tend to be less corrosive because I think there's not so much chloride up there. I'm talking about Limpopo. Limpopo is the largest reserves of platinum in the world, followed by the Northwest. And between the two, they mine almost an equal amount of platinum that's exported. You tend to find the Northwest is very corrosive. You tend to find that Limpopo is less corrosive. There's less chloride there. But the main factor is the shafts are not so deep. Instead of a gold mine that goes 4 kilometers down, a platinum mine may go 3,000 feet. Tell me that. That's about 3/4 of a mile.
Yeah.
That's very interesting. Thinking back to sort of the general knowledge of corrosion, we do know that the environment affects corrosion. And it's so interesting for me to hear that just the different mines with their different local conditions, you see such a dramatic change in the corrosion. Yes, they still have corrosion in the platinum mines, but to a far lesser extent, and the environment, the depth in this case, plays such a significant role.
The other issue, it's the environment, and it's not conditioning as such. A number of ions are dissolved in water from the rock. You get the sulfates and the chlorides, you get nitrates from blasting, but you can also get calcium and magnesium.
Yes.
And what happens in those areas with high dolomitic rock, you tend to get those dissolved. Now, they are less deleterious than the sulfate, nitrate, and chloride. So you've got what's termed a corrosivity index, which you can determine how corrosive is the water based on the relationship between the corrosive species and the non-corrosive species. Yes. So you tend to find in platinum mines, in areas like that, there's a lot more hydroxide alkalinity coming into it because of the calcium magnesium. And even though the sulfates are quite high, they offset it dramatically, and the waters are not as corrosive.
And are those less corrosive waters equivalently of a higher pH? Is there a tie-up there?
If there's a lot of sulfide around and you get an awful lot of acid water, then you have the same problem. I'm not aware of how much more pyrite there might be in gold and coal, because those are two areas that are very bad for acid water. And platinum, where I'm aware it has acid water, but I've not picked up very much on it being a huge problem.
That's interesting, because I remember from working on the platinum mines in the Rustenburg area, the northwest area, where the platinum group metals were actually a byproduct of copper and nickel mines, where those were copper and nickel sulfide ores that were being mined. So the sulfide was there in that situation. I don't know what the PGMs are associated with now in the Limpopo area. But the other thing that came to mind is that last year we had a couple of very, very interesting discussions with Anthony Turton about acid mine drainage and what it involves and the effect on the environment of this acid mine water, like you've alluded to in the coal mines, now finding its way into the wider environment. And I think it would be worth pointing our viewers to the YouTube channel to go and have a look at those discussions with Anthony, which were absolutely fascinating.
And we'll put a link into the notes to those two discussions that we did have. They were very interesting, and the entire mining influence, particularly here in South Africa, is so interesting because it has always been such a significant part of not only our economy, but increasingly of our culture. And as you rightly allude, we have this water scarce country, and yet to benefit from the mines, we need to use the water. And I guess the challenge to the mining industry is to try and find ways to clean up their act to some extent with their waters.
You've covered AMD, so I won't go into the detail, but the water treatment that the mines do is adequate in the sense that it reduces corrosivity but doesn't reduce the total dissolved solids, etc. But you can't discharge that into the rivers because you've maybe got 6,000 parts per million of total dissolved solids, and drinking water is, 1,200 or something. And that's a complete maximum. It should be far less than that. So you actually can't utilize that. What the mines need to do in the future is to be a bit more savvy in terms of their water treatment. Because of, as I said, the water stress, particularly with the local domestic water areas. And, what was it, Helen Suzman Foundation and Greenpeace predict that we're going to have a 10% shortfall in water by 2030. And they were predicting water rationing in 2025, which we hear rumours that it might well be taking place, etc. So it's a complete stress situation. So if they want to make money and they want to stay within the water regulations, the government have got very strict water regulations. I can't stand them, the whole myriad of them, and they often don't even agree with each other, but that's another issue. They want to stay within it. They need to control their water a bit more. And the only way to do that is for sulfate and calcium and iron removal. Iron's removed regularly in the Wits Basin in two places, towards the east side and the west side, where the mine water comes up. It's acid mine water, loaded with iron, and you neutralise, aerated, and down comes a ton of sludge, iron hydroxides, ferric hydroxides come out, and they just put that to landfill, etc.
I remember also seeing in the Richards Bay area, it's got nothing to do with mining, but in terms of water recovery and dealing with these high salts contents, that they've got huge waste reclamation dams, which become, I suppose, the equivalent of a slimes dam, which are calcium sulfate, where they have precipitated out the sulfates instead of allowing them to go back into the environment.
Yeah, because you either remove the total dissolved solids by biological method or a method like reverse osmosis, etc. You can do that, but that's expensive. The time may come where the mines have to do it, and they've got to manage it themselves. The other way is to utilize, as you said, calcium sulfate. Can you sell that calcium sulfate? Can you sell the iron hydroxide? If you take out the heavy metals, because the other thing that tends to get leached out is heavy metals. You get uranium, cobalt, nickel, as well as iron, etc. Can you reuse those? At the moment, they're in parts per million, but
there's definitely research in that sector at our universities, and I think there have been some very positive results doing research largely with ion exchange to get out these high value but low percentage heavy metals, and they're increasingly important because of our dependence on computers, cell phones, and so on. And so there's some positive results that I've seen in the literature. It'll be interesting to follow their story, to see whether that becomes a way of managing this effluent stream to make money out of it. Because I think you're right, we've got to purify the water better, and if we can make money while we're doing it, it might be less of a bitter pill to swallow.
Yeah, because it's a different country, but that's what happened in Zambia. In Zambia, it's mainly copper with cobalt, but they mined it for the cobalt, not the copper. But the slimes all contain selenium, gold, and silver, and they set up a precious metal plant just to remove those and utilize those, and it more than paid for itself.
Yeah, I remember Anthony making the comment that South Africa is sitting on huge uranium reserves above ground in the slime dams.
Yeah.
I think it's interesting how we've managed to take the conversation from mine waters and broaden it, because it is such a vast and interrelated topic.
It is, and the problem is that if the mines and people that utilize mine water, if they're not careful, they're going to pollute the environment. And we've come across, Krugersdorp, huge problems there with flays all being acidified. It's going to be the same problem because the Witwatersrand Basin it's got 300 kilometers of interlinked tunnels from east to west, from Nigel through to Ramfontein, etc. That slowly fills up with water every day. And when it gets to about 550 meters below the surface, the pumps kick in the center and east and west, pump out the water. Acid mine drainage, they treat it with that slimes, that heavy, high density slimes one, or they then have to find somewhere else for it, at least treat it to neutralize it, etc. But that then goes into the rivers, and it then pollutes our rivers a lot more. And it is all interlinked. It's a mining industry problem because regulation says this is what you must do, and if you're not following it, nobody owns the mines. That's the problem. Those mines are all closed, and it's the government's responsibility to run those pump stations.
Sure. Yes, it's extremely challenging and certainly food for thought. And I don't know if you have any last comments on the topic that you'd like to raise at this point, Neil or John, things about the corrosion specifically with mine waters that you feel we haven't covered adequately?
The only thing that I feel we haven't covered was flow rate, because flow has an effect on, you can double, treble the corrosion rate. And the water actually can contain solids, whether it's on purpose, because it's the tailings and you're getting wear in pipelines, or whether it's happened because all the dust has got into the circuit by accident. And you have to look out for the wear. And we talked about coatings. The coatings on the outside get damaged, but can you use coatings on the inside to stop pollution of the water from the steel, or to combat any wear that may occur from it? Simple things like rotating pipes. With a tailings pipe, it all wears on the bottom. Put a gradual bend on the pipe. Put a deflection wear plate in to deflect it. There are a number of design things that could be done
to minimize.
And the mines know what they're doing in those terms. They're there. Say, look. It's wearing there, or it's corroding there. Let's do X, Y, Z. Using anodes in heat exchanger circuits.
Yes. So certainly, if you think about all the tailings pumping and recycling and so on that is taking place, these slurry pipelines, they're lined with rubber, they're lined with basalt, and as you say, John, a lot of the really aggressive wear situations are controlled. They deliberately make the pipelines segmented, in other words, they're flanged, so that you can rotate them. They rotate them by 90 degrees every 6 months or whatever. It's just a program, so that eventually you get a uniform wear, and when it's worn out, then you replace it. Yeah. That is, to a large extent, the overall or the overriding philosophy in the industry, is that you can't prevent corrosion, you have to manage it. Yeah. And you take the most cost-effective available situation, and sometimes that is replacement.
And we didn't cover cost, but an estimate is could be as much as 7 billion rand per year for the mining industry. It employs 500,000 people, so it's a large industry. It's not a small industry.
And it's not an industry we can live without. And so we need to find ways to live with it most cost effectively and to the greatest benefit in the long term.
Yeah. Well, of course, the caveat is that predictions are that the resources will run out between 30 and 50 years, depending on the ore body. It all varies.
Yes.
Now, I've come across that before because I remember in the North Sea, the oil was going to run out in 1990 and it's still going now.
Yes.
So, you've got to take it with a pinch of salt. But basically, the time's going to come where South Africa has got to find an alternative to mining. The time's going to come.
Yes. Yeah, you cannot infinitely draw from a finite resource. I think David Attenborough said something like that. You cannot have continued expansion in a finite world. Yes. It's got to stop somewhere. And you look at all the coal mines and the slate mines and so on in the UK that have all closed down. There is virtually no mining industry there anymore.
Even though there's still coal there.
There's still coal. There's still
it's just not viable to take it out of the ground. Yeah. Plus the fact they don't want to now
for environmental reasons.
Global warming, of course. We haven't touched that subject, but that will affect the rainfall. And you may get a lower rainfall, you may get a more unpredictable and intermittent rainfall.
And more of a constrained water resource, and it's just
and more stress, etc.
More stressful situation. Well, I think that's a lovely place to leave it and reduce our own stress. And I thank you very much for joining us today. And I do hope that you'll join us again for our next episode of Engineering Thoughts.